Hello everybody, I hope you're doing well. Welcome back to another video in the Introduction to Calculus playlist. So, in this video, what are we going to be talking about today? So in the previous video, we have talked about the idea of what is a function, and we've used the function to formalize the idea of hikes, right? So at a given time, what is the elevation you're at in the hike? So we've used functions as a way to formalize, the metaphor that we've raised in the introductory video. So what else can we do with these functions, right? So it's one thing for a function to be able to tell us, okay, at a given input, what is my output? But it's another thing to start actually describing properties of the function, right? So what is one thing we can describe for a function? So let's motivate the topic of today's video, which is about continuity. So the plan for this video is to cover different types of discontinuity, which involve jump discontinuity, removable discontinuity, infinite discontinuity, and we're gonna develop an intuition for what a limit is, which will help us describe if a function is continuous or not. So let's say we have a hike like this, right? So we would have a graph, right? We would have time on the x-axis, and we would have elevation on the y-axis. Now let's say you started at t equals 0 and you were at sea level, right? Then you kind of gain elevation right here as you go, then you kind of plateau out, then you decrease in elevation a little bit. Maybe there was a bit of a downhill, right? Then you go kind of up in elevation, and then bam, this is the rest of the hike. So thinking about real life, right? You're gaining elevation here, right? Plateauing and then kind of going downhill a little bit, and then you're going uphill, and then whammo, right? You're at this elevation, right? At this time, right? So what's going on, right? So there's a couple things. Either you are probably Spider-Man or like a superhero and you just kind of jumped up like a cliff or something and gained elevation just like that in one instant. Now that's probably not as likely because I don't think any of us have superhuman strength to the best of my knowledge. But another thing that could happen is maybe our measurement device was broken, right? Maybe like the device that was monitoring our elevation, right, as a function of time was kind of broken and maybe the battery died. So the device is registering that, oh, maybe at this time you might have had an elevation right here. So there's a little break, right? Or there's a gap, right? So let me emphasize that in a different color. So let's use orange. So there might have been a gap right here, right? And this gap is what we call a discontinuity, right? Something is kind of off with this function, right? And it's not really smooth, right? So this type of discontinuity where you see like kind of a jump, right? It's actually called jump discontinuity. So we have jump discontinuity right here. And here's an example like of a function that could have jump discontinuity. So let's say we have a function. We use f of x to denote functions. So let's say f of x was this piecewise function. A piecewise function is simply like, one curve kind of is evaluated at given sets of input and another curve is evaluated at another set of input. So let's say we had a function that was kind of like, f of x equals x squared plus 2x plus 5. And this part only happens, or let's actually change the numbers to make it a little easier. This will still motivate the topic. So let's say we had a function that was like this, x squared plus 2x plus 1. And this function was evaluated when x was less than or equal to 3, right? And let's say we had another function that was kind of like 5x cubed. And this is for all other input. So what will this graph look like, right? So we have our x and y, right? So we know that x squared plus 2x plus 1, remembering factoring, this is simply x plus 1 whole squared. So we know here that, let's draw this graph a little bit better. I think we need to make some room. So what will that graph look like, right? So we'll have a graph that looks something like this. We see here that the root is at x equals -1 because that's where this first piece here equals 0, and then everywhere else it's going to be positive, right? Because when you square a number, right, whether it's negative or positive, it's just going to like be a positive number. So let's look at what is f of 3, right? So when x is less than or equal to 3, right? Yeah. Actually, let's fix this a little bit. I just realized I made a corner case error. So 5x cubed is not going to be evaluated at all other inputs. It's going to be evaluated whenever x is greater than 3, right? That way we're including everything and not having some edge cases, right? But the point is, we see that f of 3, right? This is where like the supposed jump might start to happen. So f of 3, right, equals 3 squared plus 2 times 3 plus 1, which equals 16. So at 3, right, you'll be at 16. Let's say it was right here, right? So your function, so the first piece will look something like that, right? But what is the second piece? What is, at 5x cubed, when you plug 3 in, right? It's 5 times 27. 5 times 27 is, some number, right? That is bigger than 16, right? So 5 times 27, doing some mental math, that's 135, right? So really, at the second piece right here, you're going to be at like, 135. And you're going to have a hole right here, right? Because 3 is not included as a valid input into this 5x cubed piece, right? So you're probably going to have, some cubic growth that looks something like that, right? So this is the discontinuity, right? You see at f of 3, right? It's 16 because it's the first piece. But in the second piece, right, of 5x cubed, right, you are your piece is right here, right? So there's a jump, as you see, right? Remember the gap we mentioned earlier? This is exactly what jump discontinuity is. So, and also I'm going to put the arrowheads because the functions grow up this way and that way. So this is what jump discontinuity is here. There's a clear gap right here. So this is a simple example of jump discontinuity, and you should be able to identify examples of this, and we'll go through some example problems to make sure you guys feel good about this topic. So what comes next, right? Sorry, let me make some room down here. So the next type of discontinuity that we're going to talk about is removable discontinuity. And the way I like to think about removable discontinuity is thinking about what the word remove actually means, right? So what does it mean to remove something? It means you're going to take something, you're going to take an object away, right? And it's gone, right? You've taken it away, right? So remove means to take something away. And here's an example of a function that will have this effect, right? So let's say you have a function called f of x, right? And it equals x squared minus 9 over x plus 3. So one thing you'll notice off the bat is this, right? What do we notice, right? Number one, f of negative 3 is going to be undefined. And why is that? Because if you plug negative 3 in right here, this denominator is going to become 0, and then you'll get a divide by 0 error, right? But wait a second, Karthik. Isn't x squared minus 9 over x plus 3 something we can simplify? And yes, it is, right? So x squared minus 9 by the difference of squares is x minus 3 times x plus 3. And if you don't believe me, right, or it's been a long time, right, you can kind of use the distributive property and kind of expand, this binomial multiplication, and you'll see that this is x squared minus 9. So x squared minus 9 equals x minus 3 times x plus 3, and then you're dividing by x plus 3, and then you will see that there's some cancellation going on. So f of x really simplifies to x minus 3, right? Now, because of that, technically, f of negative 3 would equal negative 6 if we could just simply remove out this term right here, this x plus 3 term in the numerator and denominator, but you get an undefined, right? But f of negative 3 is undefined, right? So what happened? Uh, so what happened was that you had a function right here, right? And, this function simplified down to f of x equals x minus 3, which is just a normal line. But what happened was the way we wrote the f of x originally made it so that we couldn't plug negative 3 in as is. And that was because you'll get a divide by 0 error. But when we simplified this function, right, we see that this is just simply a line, right? but you kind of removed the x equals -3 point, but everything else stayed intact. So what does the graph look like? You might have guessed that, first you need to draw the graph of y equals x minus 3. So you'll have the y-intercept at -3, and then you will also have an x-intercept at 3. So the line will look something like this, but then you'll see right here at -3, there's a hole, right? Because we couldn't plug -3 in, but every other number could be plugged in. So I'm going to use a different color to illustrate the hole. So right here, there's our hole. And then everywhere else on this line of y equals x minus 3, we could, perfectly evaluate it, right? So this is the removed portion. Yeah. So removable discontinuity happens when you see this cancellation going on, right? Because in effect, this cancellation is hinting or masking the fact that you've kind of removed a point, essentially, and you're creating kind of a void. So this is what removable discontinuity means. And hopefully the word removable makes sense as to why the name is fitting. And the third type of discontinuity is what we call infinite discontinuity. So let's move down here so we have enough room. Okay, and the third type of discontinuity we have is infinite discontinuity. So the way I'd like to think about infinite discontinuity is best demonstrated through a function like this. So we're going to take what's called a rational function. So let's say we had this as our example. Let's say we had a function that was, let me think of a good example. 1 over x minus 3 plus 5. Or this is equal to 1 over x minus 3 plus 5 times x minus 3 over x minus 3. Combining like terms, this is going to be 5x minus 14 over x minus 3. So what do we notice here, right? So in removable discontinuity, we had this denominator here, but we were able to kind of get rid of it through algebraic simplification and realizing that the difference in squares factoring kind of helped us. But what happens here? There's no way where we can kind of factor this 5x minus 14 in a way to remove x minus 3, right? But you might be like, but Karthik, you can't plug in x equals 3, right? Because you'll get a divide by 0 error. So when I plug in x equals 3, you get divide by 0 error, right? So what that means is that at x equals 3, the function is not defined, right? But let's think critically as to what's happening, right? Let's say we look at x equals 3 and we look at a number really, really close to 3. So let's say we looked at the number 2.9, right? So if we plug 2.9 into this function, right, doing some gross estimation, right, you will see that 2.9 minus 3 is, -1/10. And in the top, right, you'll have like about a half, right? 2.9 times 5, that should be 14.5 minus 14, so that's a half. So you have like 1/2 over -1/10, right? So that would be, so you can do the math and figure out what that value is. But let's say you plugged in something like 2.99999, right? So what will happen is this number right here, right? What will it approach, right? It's going to approach like, a number really, really close to 1, right? And if you plug 2.999, you'll see here that 2.99999 minus 3 is equal to negative 0.0000001, right? So what happens is this denominator is going to get smaller, right? And if the denominator gets smaller and the numerator isn't really affected as much, right? Focus on the denominator getting smaller. When the denominator gets really small, then you're dividing, a normal number, right, by something that's really, really small. So the number becomes really, really big, right? So, when you plug in 2.9, 2.99, 2.99999, you get big, right? Like, you get to a big number, right? And then if you plug, and now let's look at the case where you plugged in a number really close to 3, but it's like to the right of 3, right? So let's say you plugged in like 3.1 versus 3.01 versus 3.001 versus 3.00001. So what will happen, right? So first off, the numerator is going to be a number greater than 0, right? Because 5 times 3 is 15. 15 minus 14 is 1. So the numerator is going to be a positive number, right? But when you're plugging in like 3 versus 3.01 versus 3.00001, the denominator is going to be like 0.0000001, right? So because the numerator and the denominator are both positive, right? And the denominator is getting smaller, right? As you plug numbers in closer and closer and closer to 3 that are bigger than 3, you're going to see that both the numerator and denominator become positive, right? But because the denominator gets really small, right? You're dividing a you know, a normal number, right? That's not big or small by something that's really small. So you can get like positively big. And then here you're going to get like negatively big, right? Because the denominator is a very small negative number. So what will that look like? So if we have this graph right here, right? So x equals 3 is the special point right here, right? What will happen is you will have a scenario where you're going to get, you know, negatively big on this side and then positively big on this side, right? Then you're going to have, you know, some sort of plateauing right here. And I'll explain the plateauing in a bit though. But the idea is you're going to have a graph that looks something like this, right? And you see right here at this 3, right? You're getting very, very negative in this to the left. And from the right, you're getting very, 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 very big, right? So you see how here on both sides, you're kind of tending toward infinity, whether it's negative or positive, right? And here, this is the infinite discontinuity. So this idea right here, right, that you're seeing is what we call an asymptote. And this might be a word you've heard in math, but it's good to have the intuition. So this is called a vertical asymptote. Okay, so now that we've explained like the behavior you should see with vertical asymptotes, right? The other thing you need to notice about this function is think about what happens when x becomes really big, right? So let's say x became like 100 million versus 10 million versus a billion, right? Well, 5 times a really big number, right? That's positive, right? It's going to be pretty big. But 14, this minus 14 here is going to be pretty insignificant, right? And the same scenario goes with this minus 3, right? If your x is super big, then subtracting 3 doesn't really do anything, right? It doesn't really, you know, affect the number in a special way. So what happens is when x becomes really, really big, right? So you're plugging really big numbers for x, then the value of this function right here is going to approach 5, right? And also think about the case when you plug in a really, really, really negative number for x. So think like negative 1 million versus negative 10 million versus negative 1 billion, right? Well, in both these scenarios, right, both the numerator and denominator are going to be negative numbers, right? But subtracting this 14 or subtracting this 3 won't really do anything, right? So what do we observe? When we plugged in really, really large positive numbers for x, the f of x will approach 5. And if you plugged in really, really negative numbers, like that for x, you will see that f of x will also approach 5. So what we're discovering here is this idea of approaching something, right? So approaching something as x changes. Now, you might be like, okay, Karthik, I believe that if you plug in really, really big numbers, I can have a system to figure out what a function approaches, like where does a function approach? But how do you explain that in math, right? How do you explain that like, oh, I approach something, right? Without having to draw a graph, right? Necessarily. So there's a notation we use to formalize that, and this is called the limit, right? So in the above example, right, we can formalize the idea that when x becomes really, really large, you approach 5, right? And when f of x right here becomes, when x becomes very, very, very negative, right? Then you're also going to approach 5. So limit is a way to formalize what value a function approaches when x approaches a value. So in the so let's write the limit in the formal notation, right? So we write the lim symbol and we say x arrow infinity. So what this means is the limit as x approaches infinity, so when x approaches infinity, so when it's super, super big, right, of f of x, where f of x is this function right here that we've talked about earlier in the infinite discontinuity example, it equals 5. So this statement is saying when x gets super, super large, f of x will approach 5. And likewise, we can say when x approaches negative infinity, right, f of x will also approach 5. So this is how you can write limits and describe what value a function approaches when x approaches something. And I think with this limit definition, we have a powerful framework to describe, if a function is continuous or not, right? So let's talk about continuity, right? So now that we have the idea of what a limit is in the example of an infinite discontinuity, we can say stuff like this. Let's go back to limits a little bit and do another example real quick beforehand. So let's say we had f of x equals x squared plus 2x plus 5. So you can say that the limit as x approaches 0 of f of x here is going to be 5. The limit as x approaches 1 of f of x will equal 1 squared plus 2 plus 5, so that will be 8. And you can even convince yourself, right, by drawing the graph and seeing intuitively that the function is really like, approaching these values, right? So that's one way of graphically showing. But let's go into continuity. That kind of motivates the topic perfectly. So in continuity, what do we have? So we want to describe a function as continuous or not, right? So for continuity, right, let's say you had a function here and then you had a point, right? And you want to say if it's continuous at that point, right? We can't really necessarily say if a function is continuous everywhere, but we can say at what places a function is continuous at, which has some value. So let me fix this a little bit. Okay, so we have this function, right? And we have this point, and we want to say, are you continuous here, right? And the simple answer is this, right? One simple framework is, let's look at points that are close by. So let's say this is x, and this is some value f of x, right? So a function f of x is continuous. Let's call it x equals c, right? And then this will be f of c, right? So a function f of x is continuous at x equals c if three things hold. So we have three criteria that we need to check if a function is continuous at x equals c. So at a given point, right, this is how we are going to check. So first off, right, I think you can probably guess one of the first criteria, right? Number one, f of c has to exist, right? Think about the case where like we're on the hike and then we don't know what elevation we were at a given time, right? It's kind of useless, right? We can't really tell if a function is continuous if we don't even know what the value is. So first off, f of c has to exist, right? And number two, we have to check that the limit exists, right? So when we're looking at numbers that are close to x equals c, right? We want to see if we can find, okay, as x gets closer to c, right? What does f of c approach, right? So we have to consider two possibilities, right? You approach x equals c from this side, and you approach x equals c from this side. So from the right and from the left. So one way we can say sides, or what side we're coming from, is through the plus or the minus symbol. So we say the limit as x approaches c with this plus symbol. This plus symbol means from the right of f of x, right, must exist. And we also have to say that the limit as x approaches c, right, from the left side of f of x must exist, right? So that makes sense, right? You have to kind of approach something to be able to talk about, continuous, right? Think about like the intuition behind a smooth function, right? It needs to be kind of smooth at that point. So we need to be able to approach something smoothly from both the left and right. And then the third thing, which is the most powerful criteria, is the limit as x approaches c from the left of f of x, right, must equal the limit as x approaches c from the right side of f of x must equal f of c. So what is this third statement saying? This third statement is very powerful, right? The third statement is saying this intuition. So it's saying, okay, so at x equals c, we have a value f of c. So the first criteria means f of c really exists and we can compute it, right? The second criteria is telling us, okay, the limit from as x approaches c from the right and from the left must exist. That means we can figure out, okay, from the left side, right, as we're getting closer to c, and from the right side as we're getting closer and closer to c, what are we approaching, right? And the third criteria basically unifies the first and second criteria in an equality statement. And that means, and the third statement right here in the continuity definition is saying, okay, when we approach x equals c from the left and from the right, we are indeed reaching the value of f of c. So that means you can say for certain, right, that at x equals c, the function is sort of smooth or continuous. So this definition right here unifies number 1 and number 2 condition in continuity check. So that's a wrap for this video on continuity and going through examples of discontinuity. Till next time, we will cover examples of evaluating if a function is continuous, and we will also do some practice with limits. So stay tuned for the next video, and don't forget to like and subscribe. Have a good rest of your day.